I'm Norman Wahlberger. Today we're going to look at transformations of the plane, starting with translations and then moving on to rotations and reflections. This is going to be an opportunity for us to address some important foundational issues having to do with functions, maps, and mappings. And I warn you that the approach that we're going to take here is quite different from the usual treatment that modern mathematics takes to functions. It has many advantages that I hope you will consider. So naively, what a translation is easy to describe. We have our grid plane here in the usual fashion. And suppose we're looking at a translation 3, 1 by a vector over 3 up 1. Okay? So that translation moves everything over 3 and up 1. That's intuitively what we're trying to get at. So this point is moved to that point. This circle is moved to that circle. This square is moved to that square. And a line like this, L, is moved to this line, M. And you can see that because, say, this point here gets moved to there, this point here gets moved to there, this point here gets moved to there, and so on. So we have an idea intuitively and geometrically what it means. What is it exactly? How do we define a translation? Well, modern mathematics has several words that cover this kind of object, sometimes called a transformation, sometimes a function, sometimes a map, sometimes a mapping. And in most mathematics texts, the treatment would be something like this. They would say, well, tau of 3, 1 is going to be a map from the plane to the plane, from R2 to R2, and it's given by this expression, tau of 3, 1 acting on the point xy is the point x plus 3, y plus 1. This certainly captures what the transformation does. But there's a lot of things wrong with this setup. Such as what? Well, such as, first of all, it involves infinite sets. We're not interested in considering infinite sets because they don't exist. Secondly, we're working over the rational numbers completely. We have not got anywhere close to talking about the real numbers, which are very, very complicated. But that's really a minor issue. It's really this point here that we're going to look at quite differently. Because this treatment of a translation only makes it act on points. If you want the translation to act on circles or squares or any other objects, it's a secondary kind of thing that's a little bit more indirect. In other words, there's a lack of flexibility with this notion of translation that we're going to circumvent. Also, we're going to end up writing things differently. We're going to put things back to front. So let's see how we're going to approach what a translation is. So our approach is going to treat this tau 3, 1 as an expression. And we're going to specify how that expression interacts with other expressions. So the main thing that we're going to say is that if we have a point xy, then xy followed by tau 3, 1, that expression is, by definition, equal to the point x plus 3, y plus 1. So we define the translation in terms of how that expression interacts with that expression to give us another expression. Here's a more official definition. If v is a vector, then the translation by v is the expression tau sub v. And furthermore, if a is a point, in other words, if a has the type of point, then a followed by tau of v is, by definition, a plus v. Where we've defined this previously, this means the point that you get by starting with a and moving in the direction v from a. That defines a new type of mathematical object called a translation, or we'll say tran for short. So a translation is just an expression like this, and this is the definition of how it acts on a point. Now when we have something like this, there's an ambiguity, or there's a possible flexibility in thinking about it. We can think that this is the point A acted on by the translation. But we can also think of this as being the translation input with the point A. In other words, which one of these two things we consider first is up to us. The expression itself does not prefer either the a or the tau sub v. One is to the left, one is to the right, but neither of them has priority. It's just both of them together gives us the new point. Let's look at an example. If we take the point A3 and apply the translation tau 3, 1, then we add 3 to this, we add 1 to this, we get 11, 4. When we take the point 9, 1, act with the translation, we get 12, 2. Now the line L that's through these 2 points, 8, 3 and 9, 1, is this line L, 2 to 1 to minus 19. I remind you that the formula is y1 minus y2. That's the first one. Then x2 rather, minus x1. That's the second one. And this expression here is this times this minus this times this. This line has the equation 2x plus y minus 19 equals 0. But the line itself is actually that expression there. There's another situation where a mathematical object is actually just an expression. That will be very common for us. Let's consider another line, the line M through the points 11, 4 and 12, 2, namely these 2 points. That's the line 2 to 1 to minus 26 with this equation. Now, back in the first slide, these were the lines L and M that we were talking about. You can check that those points actually agree. So it makes sense now to say, well, this translation, which is moving points over 3 and up 1, also takes this line L to this line M. How do we arrange that? Well, we say that in general, if we have a vector v, rs, and a line L equals a to b to c, then we can make a new expression by taking the line L and applying the translation v. And that's going to be another line. In this example here, if we take this L and we apply the translation tau 3, 1, then we get this line M. In general, you can check that the formula is, if you translate this line L in exactly the same way as we've done here, you will get the line A to B to C minus AR minus BS. So this is the definition of how a line and a translation combine to give you another line. So we see that this translation is actually a flexible thing. It can act on points, it can act on lines, and later on we'll see that it can act on many other things. So it's not restricted to simply acting on points or acting on lines or anything else. Its definition can be extended to more and more things. Now let's have a look at how we combine translations. Combining translations is usually called composition. And here's our rule for composing two translations. So if we have tau v and tau u, v and u are vectors, then we define this expression, this combination, to be tau v plus u. That's how we define what this product of two translations is. And now one proves that for a point A, or a line L, that if we start with the point A and we apply the translation TV, in other words, if we look at this expression ATV, that's another point, and then we apply tau u to that, that's another point then. That's the same as starting with the point A and applying this composite translation TV times TU. And similarly, if we start with a line and first act with the translation by V and then act by translation by the vector U, that's the same as starting with the line L and acting by this composite translation. That means that we can write, when we have an expression like this, we can write simply A followed by the translation V followed by the translation U, which means we start with this, then we apply this, then we apply this. And we've arranged things so that the brackets are unnecessary. It doesn't matter how we bracket things, it's a consistent expression throughout. This is a very nice way of thinking about transformations. The thing we start with, then the next transformation, then another transformation if we have one, and so on. Next time, we're going to apply the same kind of thinking to reflections and rotations. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.